in order to understand this technique, if you like, of drawing stereoisomers based on the number of stereo centers, let's take another example. In addition to the example that we learned before, which was, if you remember, 2-bromo-3-chlorobutane. This time we take 2,3-dibromobutane. 2,3-dibromobutane as an example. This time, so this is 1, 2, 3, 4, 2,3-dibromobutane. If you look at 2,3-dibromobutane, you will notice that this compound has two chiral centers. It has two stereo centers. This is, of course, one of them, and this is the other one. C2 and C3 are actually chiral centers. You might predict, following the formula 2 to n, that there are four stereoisomers which we can write. So 2, therefore, so 4 stereoisomers. But I can tell you now that this is not yet finished. This story, or the discussion of this compound is not yet finished. If you look at the two chiral centers here, C2 and C3, you will notice that they are identically substituted. C2 has Br methyl group, this bromoethyl and hydrogen as groups around it. And if you look at C3, it has methyl, it has bromo, hydrogen, and again bromoethyl group around it. So both stereo centers have identical substituents around them. So they are identically substituted. Again, if you look at C2, C2 has hydrogen, it has Br, it has methyl, and it has bromoethyl. And the same thing for C3. They have C3 has exactly the same substituents. Therefore, this molecule, or the two stereo centers, they are identically substituted. This is very important. The two stereo centers here in this example are identically substituted. Again, C2 has Br, bromo group, methyl group, hydrogen, and bromoethyl, and so has C3 stereo centers. So the two stereo centers, therefore, have exactly the same groups or substituents that are identically substituted. Let's begin with drawing the first. Remember that we said initially, or we specified that the number of stereoisomers, okay, are 4. Let's begin with the first one. So, which we can draw using tetrahedral drawing like this. So this is the first one. Remember, you begin with any stereoisomer, and then after that you draw its mirror image, and then to draw the third one you simply keep or fix stereochemistry at one chiral center, and then you invert the stereochemistry on the other in order to get stereoisomer number 3, and later you simply draw its mirror image to get number 4. So that's the same practice that we follow, and that's how we should do. This is exactly what we should do in order to draw possible stereoisomers. So this is the first one. What we should do next is we draw the mirror image of it. For that, of course, it would be useful to keep track of carbon atoms, so we should number them in order to keep track of them. And then if we want to draw the mirror image of this, that should be then easier to do, because now we have numbered them. Okay. So this is, of course, we should number them accordingly, because remember, this is the mirror image of this. So this is, of course, carbon 4. That's because this is carbon 4. Simply, you just imagine you place this in front of a mirror. Okay. We continue with drawing the the mirror image, so that's exactly what we obtain. So this is stereo isomer 1, and this is number 2. So these two are the first two stereo isomers that we should draw. We begin with any stereo isomer, but then we do to get the second one, we simply draw its mirror image. Now to get number 3, we keep the stereochemistry at either C2 or C3 fixed, and then we change the other. So let's do that, okay? So to get the number 3, we fix, let's say, C2 stereochemistry, we fix it, but then we swap the positions of groups on C3. So this is again, this is 1, 2, 3, and 4. So this is stereo isomer number 3. So again, to obtain 3, you keep the stereochemistry at C2 fixed, and then you change the stereochemistry at C3 by simply swapping the positions of Br and hydrogen. After this, we draw the mirror image of this, of stereochemistry, of stereo isomer number 3, which is, and of course you number the carbon atoms like that. So this is number 4, stereo isomer number 4, following the same rules so far. Now, if you look at 1 and 2, you would notice, of course, they are enantiomers. But before that, let's determine the stereochemistry. It should be useful to us and informative, actually. If you look at C2, of course, Br has the highest priority. This group has the second. The methyl group has third. So clearly, this is 2R, or the stereochemistry on chiral center number 2 is actually of R configuration. If you look at C3, Br is number 1, obviously. That's number 2, and this is number 3, the methyl group. So it's clockwise rotation, and therefore it's also R. So this is 2R, 3R. And again, as we learned before, if this is really a correct mirror image, then the stereochemistry should be opposite at all chiral centers, because this should be an enantiomer of that. So if we have R on C2, this must be S, is it? Let's check. Now, if you look at C2, of course, Br has the highest priority, followed by the bromoethyl and then methyl. So it's counterclockwise rotation. Therefore, the absolute configuration is S. So this is 2S. That's good so far. That's opposite to the absolute configuration of the same center on stereo isomer number 1. If you look at 3, Br number 1 has the highest priority, followed by that group, followed by the methyl group as number 3, and of course hydrogen is number 4. It's already behind, so that's exactly what we need, is always to view the lowest priority group so that it's behind or it's away from us. So we need to look at the molecule from an opposite direction to the lowest priority group, as we learned before when we try to assign these descriptors, if you like, RS for absolute configurations. So for C3, it's also counterclockwise, therefore it is also S. So 2S, 3S, whereas in 1 we have 2R, 3R. So this is, therefore, it's clearly 1 and 2 are enantiomers. That's because they have opposite absolute configurations at both stereo centers in this case. So these are enantiomers. If you look at 3, 3 has 2R, of course, or the stereochemistry on C2 is actually R. If you look at C3, it's 1, 2, 3, so it's clockwise, but then we reverse because the lowest priority group is at the front, so this should be 3S. So this is 2R, 3S stereoisomer. Now, if you look at C2 here, it's 1, 2, 3, so it's counterclockwise, so this is 2S. For C3, it's 1, 2, 3, so it's just, therefore it's R. So this is 2S, 3R. And if you look at 1, 2, you would say, and you would be able to predict that 1 and 2 are related as enantiomers. So 1 and 2 are actually enantiomers. That's because they are non-superimposable mirror images with each other. They have opposite configurations at all stereocenters. Remember before we said that the two stereocenters are identically substituted. This is a very important observation. Now, if you look at this, if we take number 3, let's take number 3 and then we try to rotate C3, or we try to put the methyl group, if you like, on the same position as the methyl group on C2. If we do that, then we would get something like this. So we keep this the same, but then we rotate like that. And if we do that, the methyl group will be down. And of course, the hydrogen and the Br, if you rotate there, of course, they will orient themselves differently. So we would be able, or you will get something like that. So remember, we rotate here. The methyl group will go down, Br and hydrogen will go up. Br, of course, will be directed towards us as viewers, and hydrogen will be behind as a result, of course, of this rotation. Now, let's put the numbers again. So 1, 2, 3, 4. If you look at this stereo isomer, you will notice actually that it has a plane of symmetry. This is actually a plane of symmetry. It's like a line basically, or a mirror plane, which cuts the molecule into two halves, which are mirror images. So number 3 has actually a plane of symmetry. If you try to do the same exercise, basically this rotation exercise on C4, definitely you will find out that 4 has also a plane of symmetry. So if we rotate 4, then you would get this stereo isomer. So this is 3, this is 4. So this has also a plane of symmetry. And therefore, these two are actually identical. They do not represent different stereoisomers. 3 and 4 are actually identical. So there is no 4, therefore. It's only 3. So therefore, it's not 4. It's actually 3 stereoisomers possible. There is no number 4. It's 3 and 4 have been found to be identical. So 3 and 4 are actually identical. That's because there is a plane of symmetry. So 3 and 4 have a plane of symmetry. And therefore, since these stereo isomers have chiral centers, but they have a plane of symmetry, they are described as meso. So they are actually what's called a mesocompound. So a mesocompound is a stereo isomer that has, of course, stereo centers, but it has a plane of symmetry. So this is called meso because it has a plane of symmetry. Of course, it has chiral centers, it has a plane of symmetry. Mesocompounds are actually achiral, therefore. That's because, again, they have a plane of symmetry. So mesocompound is achiral. And of course, enantiomers are chiral. Of course, stereoisomer number 1 is chiral, number 2 is chiral, whereas number 3 is not chiral. That's because it has a plane of symmetry. Mesocompounds do not have chirality. They are alpha D, or the specific rotation is actually 0. They do not rotate plane polarized light. That's because, again, they are achiral. That's because, again, they have a plane of symmetry. 1 and 2 are enantiomers. 3 is a meso. So we can actually summarize this. So 1 and 2 are enantiomers. 3 is meso. 3, there is no 4 again. 3 and 4 have been found, or they have been found to to be the same. They represent the same stereoisomer. That's because you can convert one of them into the other. They are actually identical. And again, they have a plane of symmetry, and therefore the correct description for them is actually meso. And remember again, meso compounds are achiral. That's because they have a plane of symmetry. So 1 and 2 are a pair of enantiomers. Number 3 is meso. The relationship between any other two should be diastereomers. So 1 and 3, 1 and 3, and 2 and 3 are actually diastereomers. Diastereomers, that's because they are not mirror images. So this compound 2,3-dibromobutane represents an example of a compound which has 2 chiral centers, and the 2 chiral centers are identically substituted. There are not 4 stereoisomers as somebody might predict initially, but 3 rather, because 2 of them would be enantiomers and the third one would be a meso compound which has a plane of symmetry. If you try to draw its mirror image, it's actually the same, because if you do this rotation, you get the other one. So number 3 represents a meso compound which has a plane of symmetry. It's therefore achiral. 1 is chiral, 2 is chiral, 3 is achiral because it's a meso compound which has a plane of symmetry. The relationship between 1 and 3 and 2 and 3 are diastereomers. So this is an example of a meso compound where the 2 chiral centers are identically substituted.